Hello, everyone. Welcome back. This is the second session on application of machine learning for SideChannel analysis. We will have 3 amazing papers to discuss, and the first presentation will be given by Gabriel Zaid. The floor is yours.
Thank you very much. So hi everyone, I'm Gabriel. I'm a security evaluator at the Thales ITSF, and today during this short talk, I would like to introduce you a new kind of neural network that has been constructed from the well-known stochastic attack. So this work is a joint work with Lilian Bossuet and Amri Abra from the Berkeley Laboratory, Alexandre Venelli from NXP Semiconductors, and Mathieu Carbone from the Thales ITSF. But before starting the presentation, for those that are not aware of what an ITSF is, just in few words, an ITSF is a security lab which is responsible for the security assessment of devices that are enrolled during a certification process. So first, what I would like to propose you is to introduce you the evaluator's goal in comparison with the adversary's one. Then I will explain you why we have to adapt the deep learning methods in the SideChannel context and in an evaluation context in particular. And finally, I will introduce you our new neural network architecture. So first, before starting, even if I'm aware that maybe most of you already know what SideChannel attacks are, I just want to introduce it. A SideChannel attack is a class of cryptographic attack in which an adversary tries to exploit vulnerabilities from a system by analyzing, for example, its physical properties, such as the power consumption or the electromagnetic magnetization. And based on a set of physical traces, the adversaries will use some statistical tools in order to extract the secret information they contain. So here, we assume an adversary, Eve, that has an access to a physical device. And we also assume that our adversary can monitor the message that is manipulated by the targeted device. So to conduct the SideChannel attack, our adversary needs at least one RAM probe and one oscilloscope, such that during an encryption, a decryption, or any other kind of operation, the Eve will capture the related physical signal. And because she can monitor the messages, obviously she can capture as many physical traces she wants. So during this talk, we will assume that each of those traces can be decomposed into 2 parts. A deterministic one, here characterized by the psi function, so this is the Leakage model, and the other part is the random part included in the trace of the physical noise, and here we will assume that the z variable follows a Gaussian distribution with unknown parameters mu and sigma. So when an adversary wants to conduct a SideChannel attack, he will obviously want to retrieve the secret information that is contained into the physical traces. And if we want to translate this goal into an evaluation context, obviously we as evaluator wants to extract the sensitive information contained in the physical traces, but we want to use some interpretable methods. And obviously we have to conduct those attacks in constraint time. So through our work, we decided to investigate the following question: how can we design a deep learning neural network that follows the evaluator's goal? So typically, to conduct a SideChannel attack, 2 main solutions can be considered: the classical one, such as template attack or stochastic attack, and the new kind of SideChannel attack based on deep learning. But depending on or in an evaluation context, each of those solutions have limitations and benefits. So first, if we take a look at the assumptions that are needed to conduct each of those scenarios, we can assume that using deep learning SideChannel attacks or DLSCA seems more appropriate because no assumptions are required on the Leakage model or on the physical noise, while using classical template scenario requires, for example, some assumption on the noise that assumed to follow the Gaussian distribution. Then, depending on the targeted device as well as the implemented countermeasures, we need to conduct some preprocessing phase, such as synchronization, point of interest selection, demonstrative reduction, and so on. And unfortunately, because each of those phases needs some configuration, if the evaluator poorly configure the preprocessing phase, therefore the attack performance will be impacted, and obviously the security assessment too. While considering the deep learning-based sidechain attack is highly beneficial, is because all the pre-processing phase is automatically conducted by the neural network itself. But however, thanks to the theoretical work provided by the sidechain community over the last 2 decades, we are pretty confident in the decision-making process provided by the classical solution. And as evaluator, we clearly understand the different operations induced by, for example, the template attacks or the stochastic one. So regarding the interpretability, considering classical scenario seems more appropriate, while due to the lack of theoretical work, the deep learning side-channel techniques can be seen as black box tools. And in particular, if we want to design a deep neural network to extract a sensitive information, we need to use some, for example, hyperparameters of optimization. And this kind of task can take a long time. So in an evaluation context, such observation is not in line with what we want. So if we want to make a quick recap on our goal, we want to extract the secret information, but use with 2 additional constraints, the constraint time and using interpretable methods. And if we want to identify the optimal solution, some requirements can be enhanced. So the first one, in an evaluation context, we hope to use some interpretable methods such that no assumption are needed on the psi function or on the physical noise, while all the preprocessing phase is mitigated. And obviously, we hope that the method we use converges toward the true non-optimal solution, and all those requirements must be applied in constraint time. And one interesting observation here is that depending on the scenario we consider, so the classical one or the deep learning methods, we can observe that first, for example, for the deep learning-based sidechain attacks, only the second and the third requirement are fulfilled, while for the classical scenarios, only the first and the fifth requirement are checked. So through our work, we decided to investigate a new kind of neural network in order to satisfy the first and the fifth requirements, such that if such solution exists, we can plan as future work to improve this contribution in order to also satisfy the second and the third requirements. So as I mentioned earlier, we decided to design a new kind of neural network based on the stochastic attack introduced by Werner Schindler, Kirsten Lemke, and Christoph Parr at CHES 2005. And maybe just a brief recap of this scenario. So here we have a physical truss, such that, as I mentioned, this physical truss can be decomposed into 2 parts. Here, the deterministic part is defined by the psi function, such that the psi function is a linear combination related to the bits of y, and y defines the targeted sensitive variable. And the other part, so the physical noise, is assumed to follow Gaussian distribution with unknown parameters 0 and sigma, such that here sigma characterize a covariance matrix. So to estimate this covariance matrix, 2 phases are required. So the first step consists in finding the coefficient related to the linear combination thanks to the least square method. And once those theta coefficients are correctly retrieved, in the following part of this talk, I will define an estimation of the Leakage model as the following box in order to simplify the slides. But once the theta coefficients are correctly retrieved, we can subtract the physical noise with the related Leakage model in order to obtain an estimation of the physical noise. And thanks with a huge amount of physical trusses, we can approximate the covariance matrix and then conduct the inference stage that is needed to retrieve the information related to the targeted variable. So, okay. Based on those observations, I can introduce you our contribution. So as a reminder, we designed a new kind of neural network so that this neural network is considered as inputs, a physical truss, and the bits related to y. Before generalizing our neural network on a d-dimensional leakage truss, I suggest you a quick overview on the different operations induced for only one time sample. So let's assume that we want to approximate the noise related to one time sample. So to do so, we will use one node such that the output of this node is defined by this function. And this function is exactly the Leakage model introduced by Schindler and his co-authors at CHES 2005. And once this estimation is conducted, we can subtract the related time sample with this estimation in order to obtain an approximation of the ith bit of the ith time sample induced in the physical noise. So obviously we can generalize this observation to a d-dimensional trace. And therefore, what we want is to design a psi layer with d neurons, such that each of those neurons characterize the Leakage model related to each of the time sample. So once this psi layer is designed, we can subtract the physical noise with the related Leakage models in order to obtain an estimation of the physical noise. And because we are in a neural network structure, what we want is to assess the ability of the neural network to characterize the physical noise as well as the Leakage model. So to do so, we decided to invert all the operations induced in this first part in order to generate a synthetic trace and to assess the ability of the neural network to correctly approximate the Leakage models as well as the physical noise. We will compute the Euclidean distance between the former yellow trace here with the synthetical one. And if the Euclidean distance between those both entities is small, we can assume that the Leakage model as well as the physical noise are correctly estimated. But in our contribution, this is not exactly the neural network we propose. In particular, we propose something a little bit different. And instead of just estimating the noise, we decided to estimate the parameters mu and sigma that characterize the physical noise or the latent space. This is the same thing. And an interesting point here is that this kind of neural networks is exactly what we call in the machine learning community a conditional variational autoencoder. So here we derive a new kind of conditional variational autoencoder based on stochastic attack in order to obtain a neural network in SideChannel that we can clearly explain in SideChannel context. But this is not the only result we obtain in our paper. In particular, to obtain an estimation of the Leakage model as well as the physical noise, we have to train our neural network. So to do so, we use the elbow loss function, which is also well known in the machine learning field, but we adapt it in the SideChannel context thanks to the theoretical work provided by the community. And another important thing here is that in the machine learning community, the conditional variational autoencoder are used to generate new input data, and they are not used to provide an inference stage. So to do so, we introduce a new strategy to infer information on Y and to retrieve the secret information contained in the physical traces. I will not detail this strategy here due to the lack of time, but if you want much more information or much more detail on our work, I deeply encourage you to read our paper. And finally, thanks to the work provided by Schindler and his co-authors, we can also use some visualization techniques such as weight visualization in order to clearly understand what is the Leakage model that is extracted by the neural network. And in particular, if we looked at the weights related to those both layers, we're able to first identify which time sample leaks information. And if one time sample leak information, we can also identify exactly what kind of bits influence the most the leakages. So once we design our neural network structure, once we identify the training process as well as the inference stage, we ask if our neural network can be considered as the optimal solution. So to answer that question, we use some datasets that are publicly available, and the result I would like to introduce you here is the results we obtain on the IIS HD dataset, which is an unprotected IIS 128, and the well-known ASCAD dataset, which is also an implementation of IIS 128, but here we have also a first Boolean masking. And the results we obtain on each of both datasets can be observable here. So first, what we observe is that if we target an unprotected IIS implementation, we were able to obtain or retrieve the secret key within 300 traces, which is similar with the state-of-the-art result with the multi-layer perceptron. And this observation tells us that finally using our contribution or our conditional variational autoencoder can be more appropriate in an evaluation context because we can fully explain all the operation induced in the neural network. The construction of the neural network can be easily made thanks to the theoretical link with the stochastic attack. And we can also easily explain the leakage model extracted by the neural network, as I previously shown. But if we take a look at the ASCAD dataset, here we observe that using CNN is much better from a performance perspective. So why? As I mentioned earlier, during our work, we decided to focus our interest only on the interpretability and on the time constraint. So we didn't work on the mitigation of the preprocessing phase. So to conduct our attack on the ASCAD dataset, we had to use some combining functions such as absolute difference multiplication or the optimal multiplication. And once those preprocessing phases are conducted, we can then apply our contribution in order to extract the sensitive information. While we assume that the use of CNN or MLP, because all the preprocessing phase is automatically provided by the neural network, we assume that the combining function that is automatically found into the neural network is maybe more adapted or more appropriate than the one we use for our contribution. So in other words, if we want to target masking implementation from an attack performance only, considering the CNN or MLP seems a more appropriate solution, but we will use some black box models. So if we want to conclude about this work, finally, through our contribution, we were able to identify a neural network so that we can interpret and explain the operation induced in the neural network itself, as well as explain the exact leakage model extracted by the neural network. And thanks to the theoretical work provided by Schindler and his co-authors and the link between those both statistical models, we can easily construct the neural network. But obviously, there is many perspectives on our contribution. And in particular, if we want just to take a look at the estimation, on the leakage model or on the physical noise, we can, for example, find some more generic structure for the latent space, such that the latent space could be automatically adapted depending on the targeted device. Another example for preventing or mitigating the preprocessing phase, we can try to find some link between the theoretical work provided on the linear discriminant analysis by the SideChannel community and the convolutional layer provided by the machine learning field. And finally, if we want to converge toward the true unknown solution, one example to mention is maybe we can find solution to automatize the sample combination. But one important point, and I will conclude my talk here, is that obviously all those perspectives must keep in mind that the explainability property of our contribution is essential to the evaluation process. So if some improvement does not include the interpretability or the explainability property, therefore, in an evaluation context, the related application could be limited. So thank you very much. If you have any question, please feel free to ask.
So thank you, Gabriel. Let's first take the question from audience, please.
Thank you very much for a nice presentation. I have a question about the AES HD set.
Yeah.
I'm not sure. I think this set uses the same key for both training and attacking. If I'm wrong, then please let me know. But if I'm correct, how did you make sure that there is no bias, or how did you remove the bias?
We validate that there is no leakages related to the secret key itself.
Okay.
So we verify that there is only leakages related on the output of the ISS box, and that's the variable we target in our work. So I think that we're pretty confident that our attack is not biased.
Okay, and what labels did you use? Which leakage, like, was it Hamming weight or?
The identity.
Identity.
Yeah.
Okay, thank you.
Hi. So if I understood correctly, your model essentially estimates the parameters of a big multivariate Gaussian. Like you estimate the covariance and the means of a big Gaussians. So don't you feel that you kind of made a template attack with a bit more steps? Because that's usually what template attack do. They estimate a multivariate Gaussian and then they recover. My other question is, since you estimated this large dimensionality multivariate Gaussian, did you have numerical instability with a big covariance matrix? Because that's also usually a problem.
I'm not hear everything you say, sorry, but if you can repeat, please.
Yeah, sure. So from what I understood,
yeah,
your model estimates the parameter of a multivariate Gaussian. So my question was, don't you feel that you kind of made a template attack with a bit more steps? Because that's usually what template attack are doing. They estimate a multivariate Gaussian. My other question was, since you're estimating on a large dimension this Gaussian, usually the covariance matrix, as you encounter numerical instability issue if you have those large dimension. So did you encounter any when you did that?
Yeah, okay. So your first point, yeah, of course, if you want, you can use some template attacks as an alternative. But one really important point here is that one important point on our work is to define a baseline to get an interpretable deep neural networks in order to then improve it and insert the main important point of using deep learning techniques in SideChannel context, namely reducing the preprocessing phase as well as reducing the assumption on the leakage model as well as the physical noise. So yeah, you can use the template attacks if you want, but if we want to get a unified tool that automates all the evaluation process, using only the template attacks could be limited. So that's for the first question. And for the second one, in our work, so here to give you just an example, for the ISHD dataset as well as the SCAD dataset, the length of the traces are really small. So to validate our contribution, we only worked on those datasets, so on small datasets, and maybe using larger datasets and so larger covariance matrix could be a problem. Honestly, I don't know. We have to investigate it.
Yeah, thank you, Gabriel, for the talk. A question: we could also, isn't it possible to also try to regress the leakage with respect to 2 points, one related to the mask and one related to the mask data, and then in fact extend what you have done
Yeah.
to higher order.
Totally, yeah.
Okay.
Any other question from the audience?
Thank you. Yeah, thank you for the presentation. I have a question. Is it possible to consider noise with other distribution than Gaussian distribution? If yes, can that help
Yeah.
improve the model?
For our contribution, because we base our work on the stochastic attack, we take exactly the same assumption, so the Gaussian assumption rate for the physical noise. But if we looked at the work provided by the machine learning community, we know that there is some works, for example, here at ISTAT 2021, that some tools can be used to automatically find a suitable latent space distribution. So in other words, a noise distribution that is not necessarily Gaussian, but it must be tested. It must be tested to validate if using this Gaussian assumption is highly impacted by other kind of distribution or not.
So let's thank Gabriel again, because we don't have much time. Please take the other questions offline, and let me also invite the next speaker.
Thank you very much.
So the next speaker in this session is Marvin. The floor is yours, please.
Yeah, thank you very much for your introduction. I'm still waiting for the slides for a second. Okay. So in the next minutes, I will talk about our deep learning side-channel collision attack, which I have developed together with my supervisor, Amir Moradi at Ruhr University Bochum. Before I can start to explain our actual attack, I will have to provide you with some important background information. So during the past years, deep learning side-channel analysis has become a very powerful technique to target protected implementations. And especially profile deep learning is a very popular technique due to its similarity to template attacks. So in the first step, a neural network is trained to memorize the relation between power consumption and key-dependent intermediate value. For this, the attacker requires full access to the target device, the profiling device, where the secret key and other secret values are known. So he can then use these values to calculate the intermediate value for the labeling. This step would be similar to the template building phase. Then in the next step, the attacker uses this model to predict the label from traces of the target device and uses this prediction to calculate the secret key. This step would be similar to the template matching phase. So the main advantage of deep learning SCA is its ability to find dependencies within the trace without further ado and to combine interesting points automatically. Furthermore, profile deep learning attacks follow an easy and well-known concept, which makes it easy to implement them. On the other hand, an additional device is required where the attacker has full control of, and he also needs to have some knowledge about the underlying implementation. The first issue was solved by Timon in 2019 by presenting the first non-profile deep learning SCA. And instead of following the classical approach by training a model, which is used to predict the labels afterwards, he is using the training metrics as a distinguisher to find the correct key. So that means he is training the model the same way that I've explained before, but he is using a key guess for every training, and then he observes how the training accuracy proceeds over the number of traces. So here in the figure, you can see an example And you can see the accuracy over the number of training iterations for all possible keys. And as you can see, the accuracy for the correct key clearly peaks out the accuracies for the wrong key. His attack works well, but it requires a training run for every key guess for only recovering a small part of the key. Also, his attack relies on small range of sample points that perfectly cover the relevant leakage, which is obtained by calculating the SNR of secret intermediate values before. That means that it's not possible to perform the attack without prior knowledge. Additionally, he needs a power model that describes the behavior between the power consumption and the processed values. For some implementations, this could be just the Hamming weight of the value, but for other implementations, it's way more complex to find a suitable power model. So the problem of requiring a power model was solved with the introduction of side-channel collision attacks. And the idea behind that is that similar operations on the same data lead to similar physical behavior, meaning that similar power consumption patterns can be observed when the same data are processed by specific operations. So the target function for that should be repetitively called for smaller portions of the intermediate state and process an input and key dependent value. So a popular choice is the S box. So when a collision is found, for example, between the S box output of the first and the S box output of the second byte, then we assume their output is equal, which also means that their corresponding inputs must have been the same due to the bijectivity of the S box. By that, we can then calculate the difference between the two used keys by just calculating the first plaintext byte XOR the second plaintext byte. So when looking at existing attacks, we can see that they all take advantage of some prior knowledge, making them not applicable in a black box setting. So a black box adversary does not have any access to a profiling device. He does not have any information regarding the position of the leakage. And he also does not have any knowledge about the relation between the power consumption and the processed values. With our attack, we make a black box attack possible by combining side-channel collision attacks with deep learning. Furthermore, we propose a technique to find input-dependent samples within a trace that even works on masked implementations, such that we can target full power traces. So let me give you a high-level overview of how our attack works first. So in the first step, we train our model M with only the part of the power traces that belongs to the calculation of a specific byte. For example, the calculation of the first S box. As we do not have knowledge about any secret values, we use the plaintext byte for labeling the traces. Then in the next step, we predict the label for another part of the power trace. For example, for those sample points that are related to the processing of the second S box byte. So then with the prediction, we can finally calculate the key difference by XORing this predicted value with the known plaintext. And as you also can see from the figure here, for both steps, for the first and the second step, we are using the same trace, but just consider a different sample range. So now let's have a closer look on our attack and see why it's actually working. For that, we have defined TIX as the range of sampling points where byte I was processed and X was used as the corresponding plaintext value for byte I. Now assume we train the leakage for the first byte of our S box, but only consider those traces where the plaintext value was hex 37. As the unknown key is the same for all traces that we are using, also the S box output is the same for all the traces that are trained by our network. This results in a model M1, which provides information whether the value S-box of hex 37X or K1 was processed or not. So when we feed the trained model with a different range of sample points, for example, with the sample points that are related to the second S-box, then we will get the likelihood of a collision between the value that was processed in this trace and the values that were processed in the trained traces. So on average, we would find a collision in 1 out of 256 cases when we consider 8-bit values, such that we can then apply our previously mentioned formulas. Of course, we not train our model only with one specific plaintext byte, but for all possible plaintext values, such that our model will output the probability for all plaintext values. So at the end, we will find the collision for every trace with the model telling us the colliding value. Usually a single prediction is not enough to recover the correct key difference, such that we accumulate the probabilities over all the traces. For example, all the traces that were also used during the training phase. Now we still have the problem that neural networks are not able to handle full traces, as this would be too computational complex. So we somehow have to find the samples that are related to the processing of a specific byte. Previous works just considered a limited range of sampling points that perfectly covered the relevant leakage that was predetermined, for example, by calculating the signal-to-noise ratio. For masked implementations, this is not possible in a black box setting, as it requires the knowledge of secret values. So our solution to that was the application of sensitivity analysis, by which the output of the model with regard to some model parameter was analyzed. And this, for example, enables to provide information about which pixels contribute the most in an image classification, or in our case, we can retrieve the leaking sample points. This was also done by Timon in a similar way, but as he required a key guess for every run, his main intention was to use it as a distinguisher for the correct key. For our approach, we only need the plaintext values. So the concept works as follows. We train a large range of sample points, and after every training step, we calculate the partial derivative with respect to the input points. By that, we can then learn how much every input point contributes to the classification. This is performed for all sample points and accumulated over all traces. I've also added a more formal approach, a formal description of our approach here. So after training of each trace, we receive the loss value L, which denotes how good or bad the prediction at this moment of the training is. We can then calculate the partial derivative of this loss with respect to all the input points X. And as I already said, accumulate that over all the traces we are using. Now let me show you some of the actual results. We targeted the ASCAD dataset, which is a publicly available SCA dataset that was released by ANSI in 2018. And it is specially made to allow an easy comparison between different attacks. There are different versions available, but we focused on the first version, that it was recorded with a fixed key and contains 60,000 traces, which with 100,000 sample points each. The underlying implementation is a Boolean masked AES with table recomputation running on an 8-bit AVR 18 mega. For all our steps, we only utilized 20,000 traces. So the leakage identification technique can easily detect the leakage in a large range of sample points. So here, for example, we trained the range between 30,000 and 40,000 sample points, and we can clearly detect where the leakage is localized. In fact, 10,000 points was also the largest range of sample points that still gave us reliable results for this data set, which of course means that we have to repeat this analysis several times until all 100,000 sample points were covered. We also repeated the analysis with a smaller range of 2,000 points, such that we can then define our final range of sample points that we use for further analysis. We compared these results with the SNR results, and we observed that we perfectly covered the S-box output leakage for most of the bytes. So after we found the suitable ranges, we trained the neural network and subsequently attacked all the other bytes. So here I have visualized the key ranks when the leakage of byte 10 was learned and all the other bytes were attacked or targeted. And we can clearly differentiate between two different cases. So in the first case here on the left, we can see that the correct key difference is recovered by using only a few hundred traces. And in the other case, for these key differences, the model was not even able to recover the correct key difference by using all the 20,000 traces. So unfortunately, the key rank requires the knowledge of the correct key such that an attacker cannot obtain those figures. So this leads to the question how an attacker knows whether the calculated or predicted key difference is correct or not. And our solution to this was the application of MC dropout, by which some of the connections within the neural network are randomly dropped, and then the prediction is repeated several times. So when we then observe the same output several times, we know or we assume that the correct key difference was calculated. So one crucial advantage against the attack by Timon already becomes clear when you look at those figures. So we can recover multiple key differences by training only a single model instead of training one model for each key guess for recovering a single byte. We performed the attack for all possible combinations multiple times, meaning that we trained all 14 masked bytes multiple times and consequently attacked all the other bytes to get the key differences. This resulted in those matrices you can see here that show the portion of a successful attack for all combinations. I also have to mention that the first 2 bytes of the data set were unmasked, such that we only analyzed the remaining 14 bytes. And this is also why the first 2 rows and first 2 columns are empty. So we differentiated the attack in 2 scenarios. In the first scenario, we assumed an attacker without any knowledge, such that the leakage identification needs to be performed for each byte separately. And in this case, we were able to reveal 25% of all possible combinations of key differences. And as you can see from the figure, approximately 2 to 3 bytes need to be trained until all relevant key differences can be obtained. In the other scenario, we assumed an attacker who knows the offset between the calculation of different bytes, which he can, for example, obtain by visually inspecting the power trace. And in this case, the leakage identification only needs to be performed for a single byte, and all the ranges for the other bytes can be derived from that. The success rate was significantly higher, and we were able to recover 53% of all possible key differences. And we can also see that the majority of all trained bytes is even able to recover all relevant key differences. Now I want to show you the complexity of our attack. So in the first scenario, in the black box setting, when targeting the full trace, it takes approximately 2 hours to recover all key differences. And in contrast, in the known offset setting, only 15 minutes are required to recover all key differences. Because as I said, only the leakage identification only needs to be performed for a single byte, and one model is enough to recover all key differences that are relevant. We also performed the differential deep learning attack by Timon on our machine and only used those sample points that contained the relevant leakage. And in this case, the attack took around 1 hour and 20 minutes. To show the reproducibility of our attack, we also targeted some other publicly available datasets. For example, the ASCAD variable key dataset, which is similar to the previously targeted ASCAD fixed key dataset, but it is measured with a noisier measurement setup. So while 200,000 traces of this dataset are recorded with a variable key, there are also 100,000 traces that are recorded with a fixed key, which we targeted. But again, we only used 20,000 traces. At the end, we resulted in a success rate of 40%, meaning that we recovered 40% of all relevant key differences. And then we also targeted the DPA contest 4 dataset, which is protected by rotating S-box masking. And here we were able to obtain 84% of all key differences by only using 5,000 traces. And we also targeted an improved version of this dataset where all bytes are masked individually and also shuffling is applied. And here we revealed 44% of all relevant key differences. So now let me summarize our work. We developed a new deep learning-based methodology to attack protected implementations. Our attack combines the advantage of deep learning and side-channel collision attacks by using the power of deep learning to automatically identify and combine complex leakages. And we used collision attacks to make the requirement of a power model obsolete. The only requirement that remains for our attack is the existence of leakage, of collisions. Our leakage identification technique can find input-dependent samples without knowing any secret values, such that our attack is applicable on full traces in a black box setting. We have shown that our attack is more efficient compared to existing non-profiled deep learning attacks, making it promising against protected implementations. And if you want to try out the attack by yourself, you can also find the code on our GitHub. Thank you very much. Now I'm happy to take your questions.
So I cannot see any question in the chat. Let's take questions from the audience.
Thank you for your presentation. I have one question. How can the attacker perform this attack to the hardware implementation, which perform operation parallelly?
This is still up to open work, and we haven't tested it on, for example, hardware implementations where the S-boxes are processed in parallel. So yeah, I don't know. We haven't investigated that. But of course, it would be interesting to know if, for example, a cross-round attack is possible.
Thank you.
So any other question? So if there is no question, I would like to ask a question about what you have presented on slide number 6, if we can go back. Wonderful. My understanding is that you choose some part of the traces and you say that this is my guess. I believe that some operation is happening in this range.
Yes.
And then you gradually increase the size of the range that you are considering. Is it right?
No, not exactly. I mean, with our leakage identification technique, so the sensitivity analysis, we basically first have to find those ranges, those two, and then we can train the model with, let's say, this sample range, and use the other sample range to predict them, to predict the labels for them.
Okay, but you say that I don't have any knowledge where exactly I should look at, but I will try many different choices, right? At different part of the trace, you try the same.
Yeah, that was basically so this part where we always had a look for the sensitivity analysis at 10,000 sample points at the same time, and then we observed if we can find a clear peak in the sensitivities, and then we know that the relevant leakage must be located, in this case, for example, after approximately 34,000 sample points. And this range was then used for the further analysis.
And around that point, you are not increasing the size of the range that you are taking into account for the attack, but just the fixed size, is it right?
Yeah, for this ASCAD fixed key data set, we always use the 10,000 points, but for other data sets that contained much more sample points and where the leakage in general was higher, we were also able to increase the range up to 100,000 points, and we were still able to reveal the leakage.
Yes, thank you. There is one question in the chat panel. Have you applied linear discriminant analysis, LDA, for dimensional prediction for the full trace? If not, do you think this will have any impact?
We did not investigate that, and I don't really know exactly how this approach works, so I can't really comment on that.
Any other questions from audience? Still, we have some time for more questions. Oh, we have one here.
Thank you for presentation. I think ASCII datasets include mask, but your expression equation not to include mask, right?
Yes, exactly. We only used the plain text value. We didn't had any knowledge about masks or other secret values.
Oh, thank you. Don't worry about mask.
I mean, it worked without knowing the mask. So I think, I mean, basically the deep neural network automatically combines the interesting points that we need. So yeah, I don't worry about that.
Oh, okay. I'll see you. You are GitHub. Thank you.
So let's thank Marvin again for the nice presentation, and let me ask the other. Some difficulties I was trying to resolve it. Next presentation will be given by Jyoti. The floor is yours. Thank you.
Thank you for the introduction. So I'll be presenting the paper Whispering MLAS, Exploiting Timing Channels to Compromise User Privacy in Deep Neural Networks. This work has been done in collaboration with Manar Alam from NYU Abu Dhabi, Shalini Bhattacharya, Pabitra Mitra, and Deepdeep Mukhopadhyay from Indian Institute of Technology, Kharagpur, India. So before talking about Whispering MLAS, I would like to give an introduction about what is MLAS. So MLAS is basically machine learning as a service. So since last decade, we have seen a tremendous surge in the application of machine learning and deep learning across various sectors, including healthcare, finance, education, and so on. So very recently, these industries are moving towards something called as machine learning as a service. So this is mostly helpful for small industries, which are new in their business and cannot afford all the resources required for machine learning. Also, it's good for industries which don't want to have a ML team of their own and just want to take take help from third party service providers like Amazon, Google, and Microsoft, and so on. So it does, machine learning as a service has various benefits in that scene. So they provide like simple tools like pre-trained models, and you can deploy your models, train your models, and also design your models. And they also provide you assistance with those. So in general, the basic idea is that you kind of like deploy these models on their servers, and your clients or your company can actually access these models via some API access. So in general, these models on the clouds are implemented using some machine learning frameworks or deep learning frameworks like PyTorch, TensorFlow, JAX, and Mindspo. And these are just few of those, and there are many more such frameworks available. And what is important is to look into the security implications of these frameworks, because the data provided to these models, like the machine learning models by these industries, can be sensitive and confidential and needs to be protected. So in this work, I'll be talking about security implications of PyTorch mainly, and why PyTorch, because recently around 60% of the people are using it. So this is recent statistics from June 2023 that around 60% repositories created on GitHub were using PyTorch framework for implementing their ML models. So in this work, we have basically identified an implementation vulnerability in PyTorch, and it's responsible for something called as class leakage, which we'll be discussing further. And this is basically caused by a timing side channel, which also compromises user privacy. So the outline of this presentation. So first, I'll be discussing about the timing leakage, which I observed in PyTorch. Then I'll be discussing how this timing leakage can be exploited. And then what happens if a model is trained with differential privacy? Does this leakage still exist? And if it exists, can it be exploited? And then lastly, I'll be discussing about a cost-effective countermeasure against this timing leakage. So timing leakage in PyTorch. So let's say we have a CNN model, and we give input an image of certain class CI. Let's say in this case, it's a horse, and we get the classification result. And to get this classification result, the overall inference time for this is TCI. Now, again, we have some other image. Let's say it's of class CJ and it's class dog. And so I think there's some issue. So this should also be a CNN here. The second image is a CNN as well. So it's the same CNN model. And now this time the timing value is TCJ, and we get the classification result. So we would assume, since the network is same, the weights are same, the inference time for both the images should be same. But what we observed was that it was actually not same. And this, we term this as something called as class leakage, where the inference time for images of different classes is not similar. So I'll be discussing why do we see this leakage and what are the leakage threats which can be caused by this timing leakage, and what can be a mitigation for this. So first, I discussed the general scenario in which we are looking in this leakage. So let's say we have this MLAS server which is like on a remote cloud server, and there are multiple clients on the server. And let's say any client K in this server can give input to the model, MLAS model, and get a predicted HighLevel output. Also, the client can also monitor their inference time with user level privileges. Also, we have done all our experiments on the standard CNN models, and also the standard data sets CIFAR 10 and CIFAR 100. For our initial experiments, we had used a custom CNN model. So here's the architecture for that. And for the PyTorch, we have used PyTorch 1.9.1 CPU version. And for the systems, we have used one server-side Intel Xeon system and one client-side i7 system. So how do we do this timing measurement analysis to view this leakage first? So again, we have that same CNN model, let's say, and we pass input of certain class to this model and get the inference time. Now, what do we have to do is that for different classes, we want to create timing distributions of the certain classes. So let's say we have class CI and CJ. So for creating a timing distribution TCI, we'll take multiple images of the class CI and get the inference timing for those and basically get the TCI distribution. And similarly for other other classes as well. So let's say if there are Z classes in a data set, then we'll have total of Z timing distributions. Next, what we do is we apply for each pair of this TCI and TCJ distributions, we do a t-test. So the objective of t-test is to basically compare the means of the two groups and assess if these two distributions are significantly different or not. And we report that if the t-statistic of two distributions is greater than 4.5, then we can say with 99% confidence that the two distributions are distinguishable. So going on to the results which we observed for CIFAR 10 and CIFAR 100 datasets with the various CNN networks on Intel Xeon and Intel i7 system, we can clearly see that there are, for all the CNN networks, we can have like more than 50% of pairs which are distinguishable, like the number of class pairs which are distinguishable for both CIFAR 10 and CIFAR 100. So CIFAR 10 is denoted by red and CIFAR 100 is from blue. And this is for both systems and all CNN models. So from this, we get that, okay, we have a leakage here, but then we want to know what is exactly causing this timing leakage here. So for this, we do a layer-wise timing analysis. So earlier we were calculating the timing or like the overall timing of the inference. Now we divide this CNN into all the layers and get the timing for each layer now for the analysis part only. And so let's say we had TCI-K. So now if we have L layers in the model, we will have L timing values for each layer. And then we again get the value here. So we basically see that for all layers, the timing, the number of distinguishable pairs are less, but specifically for the max pool layer, if you see, there are two max pool layers in this model. We see that around for the first max pool layer, we have 44 out of 45 pairs which are distinguishable. And for the second, it's around 43 pairs which are distinguishable out of 45. And from this, we can make out that, okay, the max pool is the one which is having this leakage, which is causing the timing leakage. Also, to confirm whether it's only max pool or is it something common to pooling functions in CNN, we also tested for average pool. So for average pool, we observed no such leakage in the average pooling layer. So moving on, we want to see that why is this max pool function now causing this leakage? So we went into the PyTorch implementation of this max pool function and found a very simple branching statement there, which was basically the cause of this leakage. So in this branching statement, what it does is it basically calculates the maximum value for a particular window. So I'll be taking examples of, let's say, simple examples of two inputs, class X and class Y. And we'll count the number of these max val equal to val operations in each of these inputs. So let's say for the first window, we observe that we have 5 assignment operations. For the second window of the input class X, we have 3. Now going to input class Y, we have a total number of 4 assignment operations, and input class Y, again, second window, we have 2 operations. So in total for input class X, we have 8 assignments, and for input class Y, we have 6 assignments. So which is not equal. And that is the reason we are getting this timing leakage. So now, since we know the reason of this leakage, we would like to look into how this can be exploited by an adversary. So first we discuss the threat model. So the threat model is similar what we discussed before, that we have like the scenario is similar, that we have a MLAS server and multiple clients are accessing the server. But in this case, one of the clients is actually a victim for which the adversary wants to know the class label it is inferring for them in the machine learning model. And the victim is, sorry, the adversary or the spy is able to monitor overall execution time of all the processes in this scenario. And these are the capabilities. So adversary has a hard label black box access to the same model accessed by the client, accessed by the victim. It has user level privilege on the MLAs, and it also has access to manifest data set and no physical access to the system. The objective of the adversary is to infer the class labels of input data fed by the victim client to the MLAs. So now discussing the attack methodology. It's divided into 3 phases, and that is dataset creation phase, model building phase, and attack phase. So in the dataset creation phase, what does the adversary do is that it collects model inference time traces for input data, which it has, like the data which it already has, that is the manifest data set. So manifest data set is something, it's a sort of data set which is of similar distribution as the training data set, but it's not the same data as the training data set. So it takes the model, takes its own data and get the timing traces for its own data for different classes, and then converts those traces to data set format. And finally, in the model building phase, it trains a simple multi-layer perceptron label classifier for this, and then tests this data model or its own test data. When this MLP classifier is ready and giving good accuracy, it moves on to the attack phase, where it collects the victim's inference time traces. And that is like how it basically adversely measures the overall execution time of all client processes accessing the MLAS model. And again, going to the 6th step, it converts these traces to dataset format and gives it as input to the MLP label classifier. And from here, finally, we get the victim's input class labels. So this is the whole attack scenario. So we did this attack in 2 scenarios. One was single process and one was multi-process scenario. So the single process was when the client was the only isolated process running, and there was no other processes for giving out any noise. So this is a simple, this is a more ideal scenario, we would say. And we create this data set, which in one row has variants of multiple traces of certain images of a certain class, and the final label is the class label. In multi-process, what we do is we run multiple processes in parallel with the victim process. So for this, we actually did a simple forking operation to run multiple processes at the same time. And now victim is one of the processes. It's inferring for certain class C. And for creating the data set, we are taking the cumulative time of Z inferences of particular image of class C, which needs to be predicted. And this is how we like each row is D1 to like each row is same. It's same as a single process. Just the difference is this time we are taking cumulative time of Z inferences, because multiple processes will be causing extra noise while doing the attack. So now looking into the attack results. So we have first the single process attack, and this is the result for the test data. So we had 2000 test points, and we have got a 99.35% accuracy for the ideal scenario, that is the single process. Then we move to a 4-process scenario, where 1 process is the victim and other 3 are other client processes. And we see that the accuracy dropped to 91% accuracy. And this is, of course, because of the noise added by the other 3 processes. And then we also check for 8 processes. And again, the accuracy drops to 83%. And it's again because of the additional 7 processes, which are adding the noise while collecting the timing traces. So we see a successful class prediction attack. So now we stop here and we move on to something called in differential privacy, and we look how this basically what attack we did now, how it can be used to basically exploit user privacy. So first we move on to something called as differential privacy. So let's say we have a machine learning model, and it's trained on some training data, and the client is accessing this model, and it gives input and gets the inference out. And the idea is that the client should not be able to infer any information about the training dataset from the whatever output it's getting from the machine learning model. And if it's able to, and there are multiple kind of attacks which are possible if these are called as membership inference or model inversion attack, where the client basically tries to infer information about the training data. So in this scenario, differential privacy is used to train the model to guarantee that the client can access no information about the training data. So in differential privacy, what happens is there's certain noise added to the model parameters of the trained model such that there's no leakage from the output of the model. And in PyTorch, they have their own differential privacy implementation for their models, and it's called Opacus, which we used to train our models with differential privacy. So we trained all our models with differential privacy and wanted to check whether the leakage still exists. And here are the results. And we again can see that for both CIFAR 10, CIFAR 100 data sets and all the CNN models, AlexNet, DenseNet, ResNet, SqueezeNet, and VGG19, we still see the leakage here. And again, we check the cause of the leakage and it's still max pool layer. And the attack which we showed earlier is still working on this as well. So basically, we can see a successful class prediction attack with PyTorch DP implementation enabled as well. But till now, like we have not been able to break any differential privacy guarantee with this, but we would like to see if this can be broken. So for this, we try a new attack on this. And again, we have a similar threat model here with similar adversarial capabilities, but the objective is different this time. And the objective is to gain some information about the training data by this time leakage. And okay, so this time the model on this MLAS server is actually like differential privacy enabled, or like it's trained with differential privacy. So let's say we have two training data sets. One is T and one is T plus Q. And we train two CNN models with these two different training data sets. And that is M1 and M2. Now, earlier the MLP label classifier, which we had seen earlier, which was able to distinguish between classes based on timing, we again use that here. And we trained this MLP classifier with the timing data of Q, which was inferenced on M1. And next, what we did was we trained the MLP classifier with timing data of Q inferenced on M1. So that is M1 is trained on T. Now, for the testing part, what we did was that we took timing data of Q inferenced on M1. And so Q is like not a single image, it's a set of images. And the timing data of Q is inferenced on M1, and we give it as input to the MLP label classifier and observe an accuracy of 99.25%. But again, when we give this timing data of Q inferenced on M2, which it was not trained with, we see a drop in accuracy, and that is like 82.32%. Now the accuracy is 82.32% now, and this drop kind of indicates us that there is presence of Q in M2's training set. So this is not exactly a membership inference or model inversion attack, but we have certain information about the training set of the model, which of the model on the MLAS, and that breaks differential private like the guarantee of differential privacy implemented by PyTorch. So we have looked into all the attacks that are possible. Now we look into the countermeasure against this timing leakage. So the countermeasure is very simple. We had a simple branching statement. So we just convert this branching statement to a constant time implementation. And now with this, this max val equal to val and the other max index equal to index will be called at every execution for all the inputs. So hence the total number of assignment operations will now be like total of 18 and 18, which will be equal, and hence the timing leakage won't be there anymore. So now we'll again look into the results and so we see the before and after results for the CIFAR 10 dataset, and we could see that for custom CNN, AlexNet, DenseNet and VGT19, they are almost close to 0, the number of distinguishable pairs. And for others, all the SqueezeNet and DenseNet also, it's less than 50%. So that is like random. And again, we did this for models trained with differential privacy also, and there was no leakage there as well. So no class leakage after the countermeasure implementation. We also wanted to confirm whether the leakage has been gone from the max pool layer. So we did this layer-wise analysis again, and we see that there's no leakage from the max pool function now. And finally, we see the MLP attack, which we saw before, and the accuracy has reduced from 99.35% to 12% for a simple CNN model. And for a custom CNN model trained with the differential privacy, we see a drop to 13.2%. So since the MLP classifiers accuracy is dropped, we can simply say that the attack where we were actually getting information about the training data, that was Q, that will also fail because the training data would give worse accuracy for both the scenarios. So in conclusion, we have identified for the first time a privacy threat in PyTorch due to timing side channel leakage, and the leakage traced to max pool layer, and we exploited to classify input labels of using MLP classifier. We also leveraged this MLP classifier to bypass differential privacy, revealing input sets for parts of CNN's training set. And lastly, we proposed a cost-effective countermeasure to mitigate timing vulnerability. We also did a responsible disclosure of this vulnerability to Meta, and they also acknowledged the presence of it. So thank you.
We have some time for questions. Any question from the audience? I cannot see any in the chat, but I have one question. Actually, I have two. Can we go back to the results just before the differential privacy?
Okay, once. Oh, wait. Which slide?
Attack results that you have. Still, you should go back. Here, exactly. I wanted to ask a question. What happens if the number of labels is increased? Have you seen a declining trend?
Okay, so we did this only for the CIFAR 10 data set, and there we had 10 labels. But I think, yeah, the number of labels would also affect this, definitely. So yeah, less labels would be good in that case.
Advantages to the adversary. So any other question? So we have one here.
Did you looked into the CPU version of the PyTorch library? Did you also looked into the GPU versions?
Yeah.
Is this the same leakage?
Yeah,
behavior?
the leakage is still present in the GPU version as well. So we didn't mention, like, we did it recently, we checked it on GPU as well. So the leakage is less compared, like the distinguishable pairs which we observed was less compared to the CPU version. And that is also understandable because we see a lot of parallelization in GPU. So therefore, the leakage is less, but it's still there.
Thanks.
There is one question just back there.
Thank you for the talk. I have a question about like Cypher 100. They have like super class and class. So I'm curious if the time difference is like larger between super class among super class and like smaller when they within the same super class.
What do you mean by superclass exactly?
They have like a human superclass, like memo superclass, like Yeah.
Okay. So so we didn't like look into the super classes thing, but you're saying basically like they have total of 100 classes, but they are also like bigger. Maybe it reduces to the number of classes in one sense, or like increases the number of classes.
Okay, so what I meant was if they in the same superclass, there's a will the time difference smaller, or it doesn't matter?
No, yeah, so it's actually the timing difference. We didn't actually go into like how much is the timing difference between various classes, but we just observed that whether it's distinguishable or not. We didn't basically look into how much is the difference. We were just depending on this t statistic value.
Okay, thank you.
So if there is no other question, we can conclude the talks. Thank you for attending this session, and let's thank all the speakers in this session again. Thank you.